Okay, cool. Hi everyone. Today, my co-author Brian Wheatman will be giving the lecture. He's a PhD student in Johns Hopkins University. Brian, go ahead.
Yeah. Okay. Hello all. Today I'm going to be talking about vectorization, and I'm going to be tackling this from a very, well, hopefully practical and applied side. Also, feel free to interrupt or message in the chat if you have any questions or anything isn't clear. This will be more useful to everyone if questions are sort of just asked when they're had. So I'm going to start with sort of what is vectorization from a practical perspective. When is it useful? What does the compiler do for you? And how can you make the compiler do it for you? And then lastly, when the compiler can't do it, how can we do it manually? So all of these notes, as well as the code from the examples and code to build it, can be found on my GitHub. Here is the link. Okay, and let's get started. So vectorization is a style of programming where you're simply going to be applying some operation to multiple elements. It's sort of often known broadly as a single instruction, multiple data, or SIMD type programming. And to do this, the processors that we use today have both special vector registers and special vector instructions. So if we look at the standard set of registers that will exist in most x86 processors, also as a note, I will be mostly working with x86 Intel processors. This has vectorization is applied much more broadly. This code will work on AMD's x86 processors, and there are other flavors of vectorization across ARM chips and RISC chips, and likewise. But just for simplicity, I will be showing examples and using Intel's documentation. So here are sort of the base standard registers. We see these are sort of range in size from 8 bits to 64 bits, as opposed to the vector registers will often range in size currently from about 128 bits to 512 bits. Another major difference is that when you perform an operation on a register, that operation is done on the entire thing. If we add 2 registers, the result is the sum of those 2 values. This is not true for vector registers. Instead, if we're going to add 2 vector registers, we will think of these vector registers as storing some set of elements, and our output is going to be the element-wise operation, not the total. So for example, if we wanted to compare these sets of elements, we could use the instruction P compare equals D. These all of the instructions have sort of short mnemonics. So this is a compare equal D. D in this case stands for basically double, but not double as in a floating point double, double as in 2 bytes. Double size word. And so what this will do is this will compare each corresponding position, and its output, if they are equal, will be to set all of the bits in the corresponding position to 1, else it will be 0. So the output of this is another vector register. One other thing to note, doing this on a 128-bit register, so on 2 input 128-bit registers and 1 output, is 1 instruction. And if we wanted to do it with a 256-bit register, we would use different registers and a different instruction. Okay, now let's jump to a problem. So the problem we're going to look at is sort of a fairly simple problem where we simply have an array of data, some pointer to an array. It is of size, some large size. we have some target we want to find, and we want to find how many times does the target appear in the data. So something to note why this problem is good for vectorization is that we are doing the same operation on every iteration of the loop, and the iterations of the loop have nothing to do with each other. Similar for when you want to make a parallel loop for thread level parallelism. Vectorization will happen nicer when you have independent loops. So one thing to note about this code that's actually at first indication not a great sign towards vectorization is that we have branching here. Branching is not good for vector code. We need to perform the same thing in all cases. However, for a case like this code could be transformed to move this comparison inside this. And so you always add whatever this is. Okay. So just for, okay, that's out of the way. And let's view the code itself. So again, here's the code. And sorry. And we'll have a couple different versions of assembly. This is Intel style assembly. And so we're going to start with here down in the bottom left, and I will make that bigger for a second. Okay, so this is the basic unoptimized code. And so one thing we'll note, and this is sort of true of a lot of unoptimized code, is it looks, in some cases, like it does a lot of extra work. And so what it's doing here is it is clearing out some things to store registers and get all the arguments. Here is the loop with the branches to perform the if statement here and here. Also, these links to get to these same things are in the notes to follow along. Also, I highly recommend using Compiler Explorer, this website, to sort of help you look at assembly code. For example, you can do things like mouse over here, and you'll see what relevant C++ code is highlighted, just to make it sort of easier to follow through. So one thing we'll note is this sort of basic unoptimized code to process 1 million bytes on my laptop takes about 172 microseconds. So one thing we can do is we can just ask the compiler to optimize it for us with standard terms. We have lots of different flags we can specify. Up here in the top middle, we can see the first set of ones that I am using. What these flags are is we have the O3 flag. This basically tells the compiler it's allowed to use fairly aggressive optimizations. However, none of these optimizations should change any behavior of the program. The sort of O-level optimization level flags go from O0 for no optimizations, O1, O2, and O3 for full optimizations. All of these should have the same exact behavior in your code. And these are purely optimized for performance. There is also 2 additional flags to optimize code for space. These will be OS and OZ. And then the last one you may see is OFast. OFast is different in that OFast is allowed to change the behavior of your code and how it deals with floating point numbers. But other than that, the performance, the impact of these flags should purely be performance and not in behavior. So if we take a look at this code now, in some ways, optimizing this code actually made this a lot simpler. So if we sort of walk through the code, we have, here is our inner loop. In each iteration of the loop, we perform our comparison. We get the flag to get the result of the comparison. We add this to our count variable. We check if we're done, and we jump back. And that's the entirety of it. Now, one thing I'll note is I did add these other 2 sort of non-standard flags that do impact this. The first is no SSE. SSE is another flag, is telling the compiler it is not allowed to use SSE instructions. By default, the compiler will actually do some vectorization for us. And so I just use this just to disable that to give us clean unvectorized code. The other flag I'm using here is to disable loop unrolling. Loop unrolling is a pure benefit to this code. It will just make it simpler. However, it also makes the code a little more difficult to follow. And so we can see the code with a loop unrolling on the bottom. Now, one thing we'll note here, we see sort of the startup. You first check if you want to go to the loop unrolled version, and if not, you go to the basic version. Here will be the loop unrolled version of the code, where we perform 4 comparisons in each iteration. However, because n might not be divisible by 4, we will also have a cleanup loop at the bottom to do the remaining iterations. And we'll notice here that this optimized code runs about twice the speed of the original unoptimized code. Okay, the next thing is we can see on the right, this is the vectorized code. And so there's a couple things I want to point out. One, this code ends up having a lot of similar structure. One thing I'll note is I've disabled loop unrolling purely to make this code easier to read. But it does actually share a lot of similar structure to the unrolled version, because once again, each iteration of the loop is dealing with multiple elements. So once again, we're going to check if n is big, then we're going to do some setup and go into loop iterations of size 8. Else, we're going to go into the base case. So if we jump back to this, we went through all flags. So here's the vectorized code again. And now let's sort of walk through this. And I've sort of transposed that assembly into some C code just to make this a little easier to understand. Or C++ style code. So what we're doing here is the first thing, as I said, we are checking to see if we are big enough. We are then going to sort of loop over until so that we don't go off the end. We then want to compare our target. We're going to want to take our target and compare it in all possible positions. We're also going to want to store the count, and we're going to want to store the count in all possible positions so that we're not grouping these things together. Then as we iterate by 8, we want to compare it equal in every position. One slight oddity here is this minus equals. And the reason behind this minus equals is, as we saw above, the output of a vector comparison is all ones if they're equal and 0 otherwise. Now, all ones is perfectly equivalent to -1. And so if we just subtract out -1 each time, we can count it up. However, this will give us a count spread out over the entire vector. And so we then need to group this all together. And so that is exactly what we see here. We start with the broadcast out to take our target into all possible positions. We XOR to set the count register to 0 in all positions. And then in the main body of the loop, we simply do the comparison, do the subtraction, and iterate the loop. After the loop, we have to do the reduction. And the reduction ends up looking at code that looks something like this, which is simply taking out the bottom and top portions and adding and shuffling these things together. One thing to note is it does have reasonable to non-trivial cost to move things to and from vector registers. So the simple operation of summing up all of the elements in a vector register does involve code that looks like this. Okay. Now let's make a minor change to our program. One thing, if anyone took a look at this code, they might have noticed, is we are summing up the total into an int variable. This means if this n is very big, bigger than 2 billion, this code would not give us the correct answer. So let's just change that to a long. Okay. And we're going to ignore the other optimizations and focus on the vector implementation. So now this inner loop, which we see here, is now completely different. We are no longer doing the subtraction. We are no longer iterating by 8. We are now iterating by 4. And why is this? So before, when we had this as an integer, we were actually conflating two different sizes in our program. The first of these was the size of the data types we're doing in the comparison, and the second was the size of how big the count we could get. And so we knew that we could store, when we did these comparisons, they'd give us the result in something of size int, and we could store that in size int. However, as soon as this becomes a long, we can no longer guarantee that these individual 8 regions won't overflow. And so what we do instead is we perform this comparison by first performing comparison on only 4 elements. One thing to note is the X registers are going to be 128-bit registers. The Y registers are going to be 256-bit registers. The Z registers are 512-bit registers. And so in this case, we perform the comparison on 128-bit registers. So we only perform 4 comparisons. We then basically separate out these into 64-bit positions. And so we map it in this way where you take the element and basically 0 fill. And this way, as we sum up in these 0 filled registers, we now have 64 bits of total position, which is big enough for as big as count can get. Does that make sense?
Quick question, actually. It's a bit of an aside, but
Yes.
with the loop unrolling, we notice we have a constant condition, right? I is less than n, and n is known before. What happens if that condition is done
N is not known before.
as an arg? Yeah, so I'm saying like when you instead of like just when you encounter the for loop, n is fixed though, I'm saying.
Yeah.
It's not manipulated, but let's say you have a dynamic condition where inside the for loop you do change the value of n, or you have something where you access the array size or vector size, something, but you change the vector length during the execution of the for loop. How would loop unrolling account for that? When we first checked, like, hey, we're gonna execute the first 8 iterations of a loop with when it's unrolled, you would check, hey, it's less than we can do more than 8 iterations from the perspective before we've done any other statements, and then we run it. But what if the condition changes where we'd only be running less than 8?
So a couple things. One thing I'll note is changing vector size is on most architectures not possible. These are things, built into the silicon. So there are some architectures out there that do have dynamic vector sizes. These are less common. However, you could absolutely have an indeterminate end. For example, if instead of counting ints, let's just say I wanted to stop at the first one, so I don't know when I'm going to stop. So there's a couple things. One thing you can do. So okay, if you have to strictly check something, and you are not allowed to touch memory after you touch that thing, then there's nothing you can do with vectorized code. I can't make 8 comparisons at a time if after the 4th one, I'm not allowed to access the memory of the 5th one, and I wouldn't know that until I access the 4th one. That's simply not possible. However, what can be possible is basically you would always do sets of 8, and maybe you would, if you run into something and you're like, oh, I ran into this thing, I stop. When you fall back to the base loop, what you could do is you could fall back to the base loop before that vector.
Gotcha.
And so you basically, when we have this base loop, you could just say I minus equals 8 here, and then you'd stop exactly where you want to. In fact, it's not uncommon in some vectorized code, if you know it's going to be vectorized and you're not particularly pressed for memory, to pad some of your data up to aligned values so that you always can read off on blocks. And this often has very little cost because memory allocators will, with high frequency, give you memory chunks that are aligned to powers of 2. And so just giving yourself that extra memory that you're allowed to read, and maybe you fill that endpoint with known values so you know to mask it off. And so there's a couple different tricks that you can use. If it is the case, like, for example, in C-style string manipulation, where you have some byte is going to be the 0 byte, and touching any memory after that 0 byte is not safe for security reasons, then you cannot do vectorized instructions. Does that answer your question?
Yep, that was perfect. Thanks.
And I see there was a question in the chat about different strides. This was a while ago and I missed this, so I apologize for that. Is that question still, is people still here? Dennis, are you still unsure about that?
Yeah, Dennis is here. Sorry, I just didn't see the chat. You can answer it.
Yeah. So how would different strides impact the assembly code? So I'm not actually sure what you mean by stride in this. Oftentimes you'll do stride to sort of separate things out. Can you clarify what you mean by stride in this context?
You can talk to him. He's just on my laptop.
I should have he's gonna hear me from here.
Can you hear him?
Not very well.
Yeah.
You can tell me and I can tell him.
Huh?
You can come here and tell him if you want.
You can just walk up probably.
Yeah. Sorry.
Yeah. Hi, can you hear me now?
Yes.
Yeah, I was talking about this I++ thing. Basically, when we try to iterate them through the whole array, but not access the every element, but suppose every second or every third element. I'm wondering whether the whole vectorization that you're talking about now is the same or not.
Oh, if instead of I++ we had I+ equals 2 and we were only looking at even positions or
Yeah.
every fourth position. So the short answer to that question is right now, when we compare to the target, that target has the same value in every position. And the count, we are summing up the count in every position. We could, when we extract out at the bottom down here, we could just extract every second position. Obviously, this only works if our stride was a divisor of our vector size. However, doing something like that would half the relevant throughput. So this might be beneficial if you have something of size 2 or 4, but as soon as you're up to size 8, there's no benefit for doing it. So for small multiples, it sort of just works, where you just pull out the relevant portions. But like 3 would get tricky.
Thank you.
Okay.
Thanks.
Okay. So yeah, once we have, so jumping back, once we have a long here, we have this. And this is all maybe fine. We've halved our throughput. However, if we were to switch this int data to a char array, we've changed our comparison to now comparing every char. So there's been a couple minor changes. However, once again, we're only comparing 4 chars at a time, as opposed to we have 256-bit registers. We should be able to compare 32 of these things at a time. And so there are other approaches. However, I believe figuring out how to solve this one is your homework. But sort of this is the tricky part, is how can you make it so that you can neither have to extract every time, because this extraction is expensive, but also how can you get better vectorization than 4 elements at a time. Okay. Now we're going to jump to a second problem. This problem is going to look fairly similar. However, this time we're going to have an array of chars of some size, and we're going to have a target byte. However, in this case, we want our target byte to appear in 2 sequential positions, so right next to each other. Now, this problem is not as well suited towards vectorization because these things are unaligned. We're accessing both times that this might be in a line short, where we'd have an even position and an odd position, but then we'd also have this case where we have an odd position and then an even position. One other note I'll say about the code, this load 16 is just some stuff you have to do in C++, so that you can read unaligned memory. It makes no difference, and x86 doesn't care about reading unaligned memory, so it has no cost. So this looks very similar. However, if we look at the, so one thing I'll tell you with the performance, with the original problem, we doubled in performance from unoptimized to optimized, and then doubled again with vectorized code. With the unaligned bytes, we get no speed up whatsoever. It takes about 500 microseconds to process 2 million bytes with both the optimized code and the vectorized code. And if we look a little bit at what the vectorized code is doing, is it's struggling to see this pattern. And it keeps moving things in and out so that it can try to map this pattern to a vectorized way it understands. However, this is not something it can do particularly well. And this is, so with vectorized code, the compilers are constantly doing better. They are constantly changing what they do and don't vectorize, and the performance is always changing. And so right now, the compiler is not able to vectorize this to achieve speed up, but I don't know how it will be in a year or 2. But for now, we have a few options. One option would be to convert this code into a form that the compiler can handle. Another would be to just do it manually. So let's first look at how to convert this. Like, what type of code do we think the compiler might understand? Well, we know that it can do vectorization if these are aligned. We don't have these interleaving. So what if we change this to just be 2 loops? We first loop over all the even positions, and then we loop over the odd positions. And now this looks effectively like the same code we had before. Give or take some types. And we find that now we get 2 reasonably nicely vectorized loops independently. And this goes from about taking 500 microseconds down to 300 microseconds. And so we were able to get a sort of fairly good speed up without needing to do too much work, without needing to maintain any sort of harder handwritten code. Okay, moving back here. Another thing we can use is what is known as intrinsics. Now, you are perfectly welcome to write vectorized code using inline assembly. It is perfectly valid. It is not the nicest way to do it. These intrinsics are functions that are supported and provided by sort of architecture designers. So Intel has their own. So if we look, this is what a vector instruction will look like. So it will give us this function. So this is that compare equals, where it's comparing 16-bit elements in a 256-bit register. We can use it and it looks like a function. However, this function corresponds just to this single vector instruction. And then it will also provide us some pseudocode for what the definition is, so we understand it, as well as what is the cost of this instruction on different recent architectures. And if you look and follow this link, we can see that Intel has a very large list of all of the instructions that they support. And you can filter this by the type of instructions that are supported by the computer that you care about. Okay. So, now one thing I'll note, I'm going to show all of the code up front, and then we're going to dive into this one at a time. The first thing I want you to note is this code now looks disgusting. This code turns into a mess, and this is very common vectorized code. My recommendation, whenever you have to hand vectorize something, is to maintain the non-hand vectorized version. Always compare against them in debug mode. Check every time you update your computing architecture or your compiler, and hopefully get rid of the hand vectorized one as soon as you can. They can sometimes provide great speedups, and so they can be worth it. But they are significantly more difficult to maintain. They are significantly more fragile, and they will limit on what architectures your code will work on. Okay.
There's a question
now let's
in the chat.
Okay.
Yeah. Just to clarify, when we use O3 for C++, does the compiler usually try to vectorize the loops?
So when you use O3, the compiler will not always vectorize the loop. Your compiler built into it will have some default of what is the computer that the code is designed to run on. And I have found it as reasonably common. I'm assuming you're running on a reasonably modern x86 machine. My guess is by default, it will use the SSE instructions, the SSE registers. These are the 128-bit registers. However, it will not use the 256 or 512-bit registers. These are because the SSE registers were originally designed just for floating point numbers. And so they existed first, and and it was more common to assume that these things existed. To enable it, you have two different choices. You can either do what I did here, which is specify -m-avx2. And this will specify that you are allowed to use avx2. I could equivalently say -m SSE4. And this will tell it which set of instructions it's allowed to use. Another option is to use -m arch, spelled like March, which will tell you which CPU you're running on, not just which instruction set. And so you can specify march equals Skylake or whatever processor you have. The simplest thing, and the thing I recommend, is march equals native, which just means whatever machine I'm working on. I don't need to know what it is or care about thinking about which it is. But for whatever machine I'm currently running on, compile for that code. One thing I will note, if you compile on one code and you use march equals native, that same binary will not work on other machines. Your code will crash with an illegal instruction error if you attempt to run an AVX512 instruction on a machine that doesn't support AVX512, and so on for other variations. Does that answer your question? Okay. So going back to how to
Sorry.
hand vectorize.
Sorry, there's a real life question. I can repeat it. Are the intrinsics part of the ISA?
No, the intrinsics give you access to the ISA. The intrinsics are, in some sense, the intrinsics is a C function, and that C function is effectively this line of code with some inline assembly in it, with this, with some compiler magic to enforce that this always gets inlined. And so all that happens is this translates. So when you call it by compiler magic, it translates directly to this part of code. And so the definition of what exists is sort of part of the ISA, but it's just a C header file with some compiler magic. And they are a pure ease of use thing. Okay. So now looking at this, let's sort of walk through this a step at a time. So we're actually going to follow a similar pattern as we did with that splitting of the two loops, in that we're going to compare the aligned ones and the unaligned ones, or more accurately, the even aligned ones and the odd aligned ones. So we start similar to the way we did before. We're going to generate our comparison ahead of time. No need to do that inside of the loop. And then for each even aligned thing for block one, we will compare, we will load the data. We will compare that load, each 16-bit position to our compare vector. We will then do a move mask. What a move mask is takes the high bit of every byte and brings it back from the vector register to the normal register. And then we will do the same thing for the odd aligned data. Now, one thing that is odd here is when we performed this comparison here, we got all ones in all short position, and then we are grabbing out the top bit from every byte position. This would lead to the natural question, why? And this has the very simple answer of there isn't a move mask epi16 instruction. It just doesn't exist. They allow you to grab from the bytes, but not from the shorts. And so in this case, it's not a big deal. The same thing is set in both of them. We have a divide by 2 at the end. One other thing I'll note is when we have these blocks, we can count the bits from these blocks with pop count. Pop count is not, this also translates to a single instruction. This is technically not a vector instruction because it operates on normal registers. However, in many ways, it operates in a similar way. This is another ISA extension. This is a thing that some CPUs support and some do not. In this case, basically every modern chip since about the past 10 years will support this instruction. And it will simply return the number of 1 bits in a register. So in this way, we perform the 2 comparisons and we do it. And then we load out the number of equal sets from each one. Okay. And this is not what happened to my, sorry. I'm missing. Okay. For some reason, some data is not showing up. Okay, not important for that. And this actually gives us a very large speed up now. So now we are 3 times faster than the split loops thing. And sorry, let me make this a little bigger. So if we want to look at that code, here's the corresponding code. And now here is the assembly. So some things to note here. The compiler is still running on these intrinsics. It doesn't necessarily do exactly what the intrinsics say. For example, in my code here, you see I do a load, compare,
Sorry,
move
can you
mask.
give me 1 second? The lights went off and I have to fix them. Hold on.
Okay.
Sorry. Yeah, sorry about that. I fixed it.
No worries.
Good.
Okay. So here we do a load, compare, move mask. However, in the code, turns out the VP compare equals W instruction can actually take its arguments can be memory locations. And so this load goes away. And so my recommendation is to sort of write out your code as explicitly as possible, and then assume the compiler will deal with the nitty-gritty details of things like that. The compiler will also deal with things like reordering to reduce dependency chains. And so it puts the two comparisons next to each other because they have no dependency. And similarly, things like that to help you increase your sort of level of pipeline parallelism that your code can get. Now, one other thing I'll note is I have found that the compiler will often not, as you start adding more intrinsics and hand vectorization, the compiler will sometimes not do other optimizations. For example, you could add loop unrolling on top of these optimizations. It will make this code slightly faster. The compiler chooses not to, and sometimes these types of optimizations are things that must be manually put back in. This is, again, very dependent on what the size is. And so it is always worth inspecting what does the code look like, how it is. Okay. So yeah, another thing I want to note is sort of when is it when is it worth hand vectorizing? So if we looked at the table of performance from the first problem, we find this. You can, in fact, hand vectorize this problem. You can get another 10 or 20% on top of this. However, hand vectorized code becomes a lot less maintainable, a lot less portable, and a lot more fragile. And it takes a whole lot longer to write and debug. And so when you have a set of code and you have to think about whether or not it is worth hand vectorizing it, or whether it is worth rewriting to make it easier, these are all things to take into consideration. How much time do you have to write and develop the code? How many different architectures do you want it to write? How portable do you want your code to be? And how much do you really need every last drop of performance? So I would say for a problem like this, where the sort of native, where it is sort of able to naturally handle, where the built-in vectorizer can handle it, it's often not worth it, as opposed to when we go to a problem like this, where it's sort of just enough off that the built-in compiler, the built-in vectorizer can handle it. And we're talking about, 5x speedups, then the extra maintainability, the extra effort of maintainability and writing can be worth it, assuming we're on the critical path. Okay. So in summary, vectorization is there to help us sort of get more out of our chip. It can speed up our code fairly significantly. the compiler is able to do a fair amount of this for us. For things that sort of align and trivial, just, specify the flags and let the compiler do it for us. And when the compiler can't do it, we can do it manually using intrinsics. This involves sort of stepping the code line at a line and thinking about what's going on. However, it is possible, and we can achieve often significant performance over what the compiler can do. Okay, I will open it to any questions.
I didn't catch up in the split loop part.
Could you go back to the part where you split the loops and go through that again?
Okay. So when we look at this original code, the difficult thing for the vectorizer was these two sort of offset loops. However, based on looking at this code, it has no issues with just doing standard types. And this is a char now, but if I switch this to a short and I'm looping over shorts, the code has no issues vectorizing this very nicely. And so knowing that, what we can do is we make one loop, check over from position 0 to -1. So sorry, one loop starts at 0, the other loop starts at 1. So this is actually iterating over all of the data twice, which is why it takes a little over twice as long. But it is worth it because we then vectorized it. And so this just iterates over all the evens. And this is just a short comparison. And this iterates over all the odds. And again, just a short comparison. And we have the first loop. Broadcast. Here is the first loop, this whole thing with the end thing. And then here is the second loop. And it's basically the same code we saw before, just copy and pasted twice. Does that answer your question?
Also, I have another question I just want to clarify, but if I don't explicitly specify the flag MEX2, there's no chance that I can use the YMF register that is larger than 128 bits registers.
I see. Do you need to use MAVX to use 256-bit registers? Is that the question?
So yes, what MAVX2 means, and I did skip over some of this. So yeah, MAVX basically tells the compiler which flags the processor supports. So if you go on whatever machine you care about, I'm going to assume this is a Linux-based machine. And if you run lscpu or cat/proc/cpu info, you can get a big list of flags. These are the things that your processor supports. That is, these are the ISA extensions that your processor supports. Some of these are things that most these are everything that's been added to x86 since the 80s about. So some of these are very old, and every computer you run probably deals with them. For example, things like a floating point unit, the ability to do a conditional move. So sort of very basic. However, there'll also be MMX was technically the first vectorization. These are actually 64-bit vectorization. We don't use these things anymore all that much. SSE, the 128-bit vectorization, has SSE, SSE2, and then SSE 3 and 4, 3, 4, 1, and 4, 2, and AVX. And so if you, AVX and AVX2, if you don't specify this, the compiler doesn't think the computer that's going to be running the code it's generating supports this flag. And so to avoid you getting illegal instruction errors, it will not use those unless you tell it it can. And so you can either specify AVX2, or you could do -m arch equals native, and this probably won't work. It did work. And this is a little silly because I right now have no idea what computer this is running on. Apparently it supports AVX2, but it's not recommended because the compiler explorer doesn't guarantee anything about what server I'm running on. So I leave it as that. But without me telling it, it's not going to generate those instructions because you can run into illegal instruction errors. Now, so here it is. If you, just for comparison, here is the flags list on a much more expensive Intel server. And so this will have some additional factors, which is mostly the AVX512 instructions. And so these guys, these guys, these guys, and these guys are all sets of instructions that do not exist on my laptop. And thus, if I ran code that tried to use any of these instructions, it would simply crash. Even if these instructions are not using 512-bit registers, they also involve instructions on smaller registers that would still crash my computer. Well, crash the program.
Sorry, I think you had a question.
You mentioned like when you're using the extension internships or flags, you crash the computer. Won't using the say AVX512, for example, and the architecture doesn't support it. I was under the impression that the compiler would break it down to some other supportable instructions instead of actually using it.
I see. If you set, sorry, let me try to rephrase the question. You can tell me if it was right. Suppose that you had like AVX512 instructions. Can the compiler break it down into smaller vector instructions?
Which the architecture supports.
Which the architecture can support?
No.
Okay.
The compile, so if you try to use a AVX512 instruction over here, for example, if I just and you then compile it for AVX2, it will simply say, I don't know about that function. Like that, it doesn't work, unsupported. The compiler will not do those transformations for you. Now, if you don't write hand vectorized code, for example, on this code, which I didn't hand vectorize, and we switch this to 512F, then suddenly it is using some AVX512. And I can tell that because it's using some Z registers. And so with this code where we didn't do it, it is perfectly happy to generate us AVX512 instructions because we didn't specify anything. And so it will figure out whatever it thinks is best. However, when we start specifying things, it will not work. And so if I just switch this to AVX, it will give us an arrow, which let me make bigger so you guys can read, which is you've specified this function, which requires AVX2, but it will be inline into a function that is compiled without support for AVX2. So it will not do the translations that you need to do to make this a corresponding SSE2 or an SSE version with 128-bit registers. Does that answer the question?
Mm-hmm. Yes.
So why is the first version cannot be vectorized?
Why was it hard to vectorize the first version of count pairs? Is the question?
Oh.
Yes.
Hard to vectorize might be the wrong term. It is not something the compiler knows how to vectorize. The compiler basically pattern matches code into things that it knows how to vectorize. And so if we were, I believe the first time I gave this lecture, I was on Clang 8, it had no idea, and it just gave you serial unvectorized code. You see here. At some point, I think by 11, nope, not by 11. At some point, somebody implemented the pattern matcher that was able to reasonably match this code. More recent than I thought. That was able to do something with it. It turns out that this is not a performance win, but it just has someone figured out the correct transformation in a very general, broad sense. Now notice this with these offsets, where we're comparing things of size 2, but shifting over something of size 1 is just more complicated and less common than when we're going to compare something and move over the same amount. So hard might be wrong. If somebody cared a lot about this problem and sat down and implemented this pattern into the compiler, then the compiler would know how to do this. I mean, this is reasonably what happens. People find an optimization, and if they care, they can try and implement this into the compilers for the compilers to always be able to do that sort of optimization. But until that's there, and if you don't want to fix up the compiler to fix your code, that's when it's worth doing transformations or doing hand vectorization. So yeah, hard, again, you can decide for yourself how hard is it to write code like this. I would argue that it is harder to write and harder to read than this code. But it's about the compiler doesn't have the correct pattern match to deal with it.
Did I answer the question?
But I have another one.
Mm-hmm.
I remember you said in the final version, you manually wrote the vectorization code, and you said the compiler doesn't do some other optimization for you, like loop unrolling. But I think that's because you specify that flag.
Oh, if you remove the funroll loops flag here in the intrinsics version, would you get it to unroll?
Sometimes yes, sometimes no. In this case, no.
There's no, right?
Yeah.
Why do intrinsics make it harder for the compiler to do that?
So compilers in many senses are not about global optimizations. Compilers are often about lots of heuristics stacked together. And so there is some heuristics that are saying, like, this is already going step by 32. We probably don't need to vectorize it more than that. It's possible if we added unroll. It's possible we can convince Clang to unroll this loop. Unroll. No, I don't remember the command. So sometimes you can convince it to, but by default, it is choosing not to.
So is it because the increment of the index here is 32? If we use a smaller one, then the compiler can still unroll the loop.
Is it because the loop index is 32? If you made it smaller, would it be possible to unroll it?
Which,
like
I
on
mean,
8, I plus equals 32. If you went up by smaller increments, would it be easier to convince or like maybe the compiler could easily automatically unroll it?
Well, I have to go up by 30. The code is incorrect if I go up by less than 32, because I'm looking at 32 bytes at a time.
Yes, but like had you written it in SSE, for example?
Yes, the compiler will sometimes do it. The compiler will sometimes not do it. I'm saying I find it tends not to. I also see a question about LVM versus GCC. Let's take a look. Here is GCC. Here is LLVM. They are not exactly identical. They are very, very close to identical. They don't change in any meaningful way. But similarly, if we go back to the one that Clang was not able to do and we switch over to GCC, GCC does nothing with it. And so for the ones that it's able to do, they're both able to do. For the ones they weren't able to do or weren't able to do successfully, neither of them do anything with it. There is sometimes you'll find differences, but I don't think you find differences all that often.
Sorry, there's one question. Let me forward it to you 1 second. Yeah. Does that mean every compiler is the combination of different heuristics that people added in? And I said yes.
Yes.
Yeah, like do
Yeah.
you remember in the first lecture I was showing you about like Prostein's law? And like how like basically you compile with like O0 and you compile with O3. The difference between that is like compiler development for the past 30 years or something.
Okay.
And it's just like people came up with optimization and then they implemented it in the compiler pass. And also there's a difference between like compiler has different passes to do different optimizations, and the order in which you do the passes also matters.
Yeah.
So for example, like if we look at some different decisions that these both had, this does compare, move mass, compare, as opposed to compare, compare. What Clang is attempting to do here is to reduce, to interleave different instructions that don't have dependencies. And so this guy depends on this guy, and this guy depends on this guy. And so ideally you run this in between, as opposed to GCC has decided not to do this. However, these are also out of order processors, and this interleaving can also happen in the hardware on the processor level. So I wouldn't be surprised if these run at exactly the same speed. And so like they will make decisions, and someone's tried to do different things in both of these implementations. And from looking at them, I would bet these run at very similar speeds. But like without benchmarking, you can't know. But yes, compilers for the most part, like what is the trade-off between bigger unrolls and smaller unrolls? There is some math you can do, but it's also just a lot of heuristics.
If there are no more questions, I guess that's all for today. Are there any more questions online? Are we good? Cool. Thank you.
Okay.
Sorry. Oh wait, there are questions. Hold on.
Oh, someone.
Oh no, these are just the open ones. No, this is good. Thank you.